For my reinforced concrete video, I used concrete material properties as seen in this paper by Hafezalgorani et al. They model a few different grades of concrete, but I'm going to focus on the B20 standard. I didn't have any real knowledge of concrete standards before making this video, but apparently the B stands for béton, which is French for concrete, and the 20 is the maximum compressive strength in megapascals. To set up the concrete damaged plasticity, you need to start with these parameters. In this graph, the flow potential function represents the relationship between hydrostatic and deviatoric stresses, contributing to the yielding behavior of concrete. For isotropic materials, hydrostatic uniaxial stresses do not contribute to yielding, so you're left with the deviatoric stresses on the deviatoric plane, which describes the shear capacity of the solid. The dilation angle is the angle of internal friction of the material, and values between 30 degrees to 40 degrees are recommended. Flow potential eccentricity is a small positive number that defines the rate at which hyperbolic flow potential approaches its asymptote. FB0 to FC0 represents the ratio between the concrete strengths for biaxial and uniaxial loading. Yield stresses in the deviatoric plane correspond to different values of K. When K equals 0, it's spherical in shape. K is the ratio of the second stress invariant on the tensile meridian, QTM, to that on the compressive meridian, QCM, at initial yield, and are plotted as a yield surface on the deviatoric plane. In Abaqus, the default value of K is 0.69, which gives you this failure surface, which kind of looks like a Dorito, but it's really more pyramid-like in 3 dimensions. And finally, the selection of an optimum viscosity parameter significantly improves performance of convergence and reduces analysis time of numerical simulations of reinforced concrete. The optimum value of the parameter can be taken as 0.0005, giving very accurate numerical results in terms of load displacement behavior. Above that, numerical results become distant from test results. In my example, I'm just going to use the default value of 0, as this particular model doesn't take long to run and doesn't have any convergence issues. Now we're getting on to our stress and strain values, which define the behavior of the material. You'll be familiar with a typical stress and strain graph for concrete under compression. We have our elastic region up until we reach our yield stress. Then we start doing permanent damage in the plastic region. We reach our ultimate strength, and from that point on, it's softening. The data from the previously mentioned paper lets us know what the yielding response should look like once we've hit our yield stress, so that data represents this region. Also to note, Abaqus interpolates linearly between the data points provided to obtain the material's response, and assumes that the response is constant outside the range defined by the input data, and the material will deform continuously. I've added a link here where you can download a text file with the values for yielding behavior. And finally, just a reminder to return to the reinforced concrete model video if you want to see the results of implementing these values.